Chapter 17 is concerned with electrochemistry, and it starts off fairly gently with a review of redox chemistry. So we studied redox chemistry in Chemistry 161, and we noted that there was an important class of reactions called oxidation-reduction reactions, or redox reactions, that involve the transfer of electrons. So looking back and reviewing some of the terminology that we had, we said that the loss of electrons is called oxidation, and that the gain of electrons is called reduction. So typically you might have two reactants. So maybe you've got reactant 1 and you've got reactant 2, and then they go on to form some products. What's going to happen is some number of electrons, let's call it n, will get transferred from one reactant to the other. So one reactant will lose electrons and undergo oxidation. In this case that would be R1, and the other reactant will gain some electrons and undergo reduction, which in this case would be R2. There's a little memory aid that we can use to help us keep track of what these terms mean, and that's oil rig, where we're writing that to indicate that oxidation is loss, oil, reduction is gain, rig. So a typical example of a redox reaction would be the combustion of magnesium metal. So what happens is when we react solid magnesium metal with gaseous O2, we form the ionic compound magnesium oxide. So we can break a redox reaction into what we call half equations or half reactions to see more clearly what's going on. So we're going to write one of these reactions for each of our reactants. So our magnesium is being converted into magnesium 2+ ions, losing 2 electrons. And then our half a mole of O2, what's happening to that is it is gaining 2 electrons, forming 1 mole of oxide ions. So what has happened is 2 electrons got transferred from our magnesium to our half a mole of O2 molecules. It was the magnesium that caused the O2 to become reduced. So it is referred to as the reducing agent, and it is the oxygen that caused the magnesium to become oxidized. So it is referred to as the oxidizing agent. So you've had all of this terminology before, but it might not be at the forefront of your mind, and you may need to kind of spend a little bit of time and just read through this section 17.1 really carefully. So you probably remember that in order to help us keep track of how electrons were moving in a chemical reaction, we developed a system called oxidation numbers. And how this system works is that every atom that is present in our reaction, or every ion that is present in our reaction, is assigned a quality called its oxidation number. And there were about seven, depends on exactly how you define it, but there are a series of rules for defining oxidation number. So you will need to relearn the oxidation number rules and learn how to assign oxidation numbers to elements and ions. So we're just going to quickly go through the rules and give you a few examples. This rule is probably the most important one. It says that the sum of the oxidation numbers of all of the atoms that are in a compound always adds up to 0. So that's a really nice rule, because if you have one atom that you don't know the oxidation number for, you can figure it out via difference. So for example, if I have this compound here, NH4Cl, then and I know that Cl has an oxidation number of 1, that the hydrogens have an oxidation number of +1, and then I don't know what the oxidation number of nitrogen is, I can solve for the oxidation of nitrogen using this rule. So X plus 4 lots of +1 plus -1, all of that has to add up to 0. So that's going to allow me to solve for what X is. So X minus 3 equals 0. So that means that x equals plus 3. So I was able to solve for the oxidation number of nitrogen in this compound in this way. So I really like this rule. The second rule is kind of related to this one. It says the sum of all of the oxidation numbers for a polyatomic ion is equal to the charge on the ion. So if I have something like CO3 2 minus, and I know that the oxidation number of the oxygen is minus 2, but I don't know the oxidation number of the carbon, then I can solve for this because I will go x plus 3 lots of minus 2, and instead of this time it adding up to 0, it has to add up to the charge on the ion, which is minus 2. So x minus 6 equals minus 2, x equals plus 4. So that's also a really, really handy rule when we're dealing with polyatomic ions. This rule here is, always a great one to know because it reduces the amount of work that you have to do. The oxidation number of any uncombined element is 0. So super easy to apply. H2, it's an element, so that means the oxidation number equals 0. I2, that's an element, oxidation number equals 0. Mg, there's no charge there, oxidation number equals 0. So super, super easy. The third rule is kind of related to the second one, and it gives us the oxidation number of a simple ion. By that we mean a monatomic ion, just an ion made from a single atom, is equal to the charge on the ion. Now this is really useful for metals because metals are always present in compounds as the ion. So I really like that. So whenever we see a sodium, because sodium always forms a +1 ion, we automatically know that the oxidation number is +1. So I really like this rule for helping me assign oxidation numbers of metals in compounds because metals are always present as ions in compounds. Okay, the fourth rule is just really a statement of fact, and it just says that fluorine always has an oxidation number of -1 without exception. So that can be useful if I have something like HF. I know that the fluorine is always -1. I can let hydrogen equal X. So X -1, it's not a polyatomic ion, so it has to add up to 0. X equals 1. So that can be really, really useful. You always know that the oxidation number of fluorine in a compound is going to be -1. So that's cool, all right? It's really, really cool. So if I had something like this compound, ClF, fluorine is always going to be -1. Chlorine X, X -1 equals 0. X must equal +1. Super simple. Okay. Now there are a series of rules that relate to specific elements. Most of the time, hydrogen in a compound is +1. Exceptions are when it is combined just with a metal. In that case, it's -1. These are called metal hydrides. Similarly, most of the time, in a compound, oxygen will have an oxidation number of -2. There's an exception, though, for hydrogen peroxide, H2O2, in which it has an oxidation number of -1. So these two things you just have to remember, okay? So you just have to remember these two exceptions here. Okay. Again, this is a series of rules that relate to specific elements. So unless combined with oxygen or fluorine, chlorine and bromine always have an oxidation number of -1. So I don't use this rule that often. Most of the time it's not needed. So for example, I can show you here that it isn't needed. Calcium is +2 because it's a metal, so it's always an ion, and calcium is in group 2. Now I could memorize that chlorine was -1 in compounds, unless it's with oxygen or fluorine, but I could also just let that be x. So then I would say that 2 plus 2 lots of x adds up to 0. 2x equals -2, therefore x equals -1. So this rule is kind of like, it's kind of handy to know, but it's not essential if you can't memorize it. Okay. So once we understand about oxidation numbers, we can redefine oxidation and reduction in terms of oxidation number. So oxidation can now be defined as an increase in oxidation number, and reduction can be defined as a decrease in oxidation number. So that makes it really easy to recognize whether something is being oxidized or reduced. So going back to those two half reactions that we had before, magnesium went from the elemental form to the ionic form, and the oxidation number increased by 2, so that told us that it was an oxidation. If I look at my oxygen, we had the elemental form of oxygen becoming the ionic form of oxygen, and the oxidation number decreased from 0 to -2. Reduction in oxidation number tells us that reactant underwent reduction. So it's really helpful when it's not obvious whether your reactant is losing or gaining electrons. There are a bunch of half reactions written out, balanced in your book. These appear in a couple of places. They appear in chapter 17, and they're in a slightly different order, and they also appear in the appendix. So the ones that appear in the chapter 17 are listed in order of decreasing reduction potential, and we'll talk about that later on. The ones that are in the appendix are in approximately alphabetical order. Now, I just want you to be aware that you'll see things in here where some of them are clearly in acid, and then others are clearly in basic conditions. So here's one in that's in basic conditions. So if you are doing any problems where you're using these standard half or common half reactions, then you do want to make certain that you select the right one with the correct acid-base conditions. Something else to note about these tables of half reactions is they're always written in the reduction direction. That is, they always have electrons on the left-hand side. If you want an oxidation reaction, you will have to flip your half reaction from this table. So one way that we can balance half reactions, that you haven't actually seen this before, is to combine half reactions, and that'll give you the net ionic equation for a redox process. So sometimes that can be kind of a quick and dirty way of getting a balanced redox reaction, is to just pull some half reactions from these tables. So this example illustrates that. It says write the net ionic equation describing the oxidation of sodium by chlorine. So sodium is going to go to Na plus, is going to get oxidized, and then the chlorine is going to get reduced. So we would have to identify half reactions that that kind of correlate to those principles. So first we identify that chlorine is being reduced, so we got to find the reduction half reaction for chlorine, and sure enough, there it is. Now we are going to have a little bit of difficulty because we're not going to be able to find the oxidation reaction for sodium. What we are going to be looking for is the reduction of sodium ions to sodium, and then we'll flip that. So we need to identify the oxidation reaction of sodium solid, but when you look in the appendix or in the table that's in the chapter, you find that you're not going to find what you want. You're going to have to find the reduction half reaction where the sodium is not the reactant but is actually the product, and then flip its direction. So once I've got my two half reactions, you'll see here that in the chlorine half reaction, 2 electrons are being consumed, while in the sodium half reaction, only 1 electron is being produced. So what I got to do there is multiply my second one by 2. So I got to have the same number of electrons being lost by whatever is being oxidized as the number of electrons being gained by whatever is being reduced. So in this case, I got to multiply my oxidation or my sodium reaction by 2 before we can add these guys together. So then now we can add these together, cancelling electrons, and we get our overall balanced redox equation. So we haven't seen this before, but sometimes, if it's a really simple reaction, you can balance it by pulling half reactions from a table and then combining them. Now, those tables, as I mentioned, normally contain only reduction half reactions, so you will need to reverse the direction of one of them before you can use it. The approach that we learned in Chemistry 161 to balancing redox reactions was this 8-step process, and this is reviewed with a nice example in chapter 17 of your book. But it's fairly complicated. It's not too bad for an online class where you have open note tests. You can just have this list open in a tab beside your while you're doing your work. But it's relatively complicated. At some point in time, you did know it because you did Chemistry 161, but it's probably a little bit too much to think that you're going to be able to perfectly recall it in the middle of a test if you don't review. So I would encourage you to review. So I'm going to run through the example that they give in the book now so you can see how this is applied. So the first step of this process is to break your reaction into 2 half reactions. Then you're going to balance each of those half reactions for elements other than hydrogen and oxygen that may not be necessary. And then you will balance each half reaction for oxygen by adding water. Once you've done that, you're going to balance each half reaction for hydrogen by adding hydrogen ions. And then you'll balance each half reaction for charge by adding electrons to the more positive side. Once you've done this, you'll examine your half reactions and you'll make certain that electrons that are being lost equals electrons that are being gained. And if that is not the case, you will multiply one or both of your half reactions by a whole number multiplier until it is. Once you've got your electrons balanced in both equations to be the same number, you'll add together those half reactions, cancelling wherever it's possible. So at that point, if you are in acidic media or it doesn't mention that or non-aqueous media, it makes no mention of acid or base, then you're done. However, if it told you that you were in basic media, then you need to convert to basic conditions, and how you do that is by adding 1 hydroxide ion to each side of your balanced redox equation for every hydrogen ion that is present. Then it kind of gets complicated. You will combine hydroxide ions and hydrogen ions to form water, and you just kind of cancel wherever possible. So make sure you kind of review this because you probably don't remember it from Chemistry 161 that well. It's pretty complicated. I'll do an example now. So this is the example that's given in a book, so you can also look at it there in text form. So it says, write the balanced equation representing the reaction between solid copper and nitric acid to yield aqueous copper 2 ions and nitrogen monoxide gas. So you don't need to know what one's oxidation and what one's reduction. That'll kind of work out in the end. But the copper reactant is forming copper 2+ ions, and your nitric acid reactant is forming nitrogen monoxide. So we've done step 1, breaking into 2 half reactions. Now I'm going to balance the copper half reaction. So it says balance for atoms other than oxygen and hydrogen. There aren't any, so it's already balanced. Okay, then it says balance for oxygens by adding water. There's no oxygen, so it's already balanced. And then I have to balance for hydrogen by adding H+. There are no hydrogens, so that's not an issue. And then it says balance for charge by adding electrons, and we're going to add the electrons to the more positive side. So on the left here, we've got 0 charge. On the right, we've got 2+. So how do I get these two to balance? I'm going to have to add in 2 electrons. So at that point, my oxidation half reaction is balanced. So now I'm going to move on and do my reduction half reaction. So the top one there is balanced. Okay, so now balance for atoms other than oxygen and hydrogen. One nitrogen is already balanced. Balance for oxygen by adding water. 3 oxygens on the left, 1 on the right. So I'm going to add in 2 waters. Now the oxygens are balanced. And then I've got to balance for hydrogens by adding hydrogen ions. So 1 hydrogen on the left, and then 2 times 2, 4 hydrogens on the right. So I need to add in 3 hydrogens over here. Now I've got to balance for charge by adding electrons. So on the left, I've got a 3+ charge, and on the right, I've got 0 charge. So I always add electrons to the more positive side. So I need to add 3 electrons over here. So what I need to do now is to make sure that the electrons that are being lost in my oxidation equal the electrons that are being gained in my reduction. And they don't. And that means that I have to multiply one or both sides by a whole numbers until they're equal. So I've got 2 electrons being lost, 3 being gained. So I'm going to have to multiply my oxidation by 3 and my reduction by 2. So that means that everything in here gets multiplied by 3, and everything here gets multiplied by 2. And now I can add them together. And the first thing I always want to check is that my electrons should cancel. So my 6 electrons do cancel. Okay, so I've got 3 coppers plus 6 hydrogen ions plus 2 nitric acids gives me 3 copper 2 pluses plus 2 NOs plus 4 H2O. So if I check everything now, coppers, I've got 3 on the left, I've got 3 on the right. Hydrogens, looks like I've got 8 on the left, and I've got 8 on the right. And then finally, nitrogen, or not quite finally actually, nitrogens, I've got 2 on the left, I've got 2 on the right. Oxygens, looks like I've got 6 on the left, and then we've got 2 plus another 4, 6 on the right. And then I always want to check the charge. 6 plus on the left, 3 times 2 plus, 6 plus on the right. So my reaction is balanced. Now, this is, the nice thing about doing this process is if you got it, right? You know that, whether you need to go back and check your work or not, because you can always check at the end whether it's balanced. So that's cool. Do I need to convert this to base? Nope, because it just says that it's in acidic condition. It makes no mention of base, so we're fine there. All right, so you've got some things to review: assigning oxidation numbers and balancing redox reactions, but it's exactly the same as what you did in Chemistry 161. So worst case scenario, pull out your 161 notes and have a look at that.